Hey, this is Miss D. These are your notes on waves. Energy can travel in these things called waves, and here's some example of some waves. Light travels as a wave, sound travels as a wave, X-rays are waves, microwaves, gamma rays, infrared waves. There's all these different types of waves, and we're going to look at the basic form of the waves in these notes. So there are two types of waves. We have transverse waves, and we have longitudinal waves, and the longitudinal waves are normally called compression waves, and you'll see why when we get to the picture of them. So let's look at our transverse waves. In our transverse wave, we have the wave moving from the left here to the right. So you can see the wave is going to go like this. See, it moves from left to right. But at the same time, it's vibrating up and down. So it's moving up and down and left to right at the same time. So it moves up and down, and it's moving perpendicular to that at the same time. That's how you can tell that it's a transverse wave, because it's moving, it's got that up and down and that perpendicular motion at the same time. All right, so let's label the parts of the wave. First we have the crest of the wave. Then we have the trough, or the trough of the wave. That's the bottom of the wave. Then you have the height from the top of the wave to the resting point, or it could be from the bottom of the wave to the resting point because it's the same height. That's called the amplitude. So those are the three basic parts that you need to know of a wave. Now, if I wanted to look at the crest at the top of the next peak, which is right there, and I wanted to measure the distance between that crest and the other crest, that would be the wavelength. And we're going to talk about the wavelength for a second. But first I want to say that this wave, this transverse wave, the easiest example of a transverse wave is light. The light that you see around you travels as a transverse wave. So let's go back to that wavelength, and let's look at the variable for wavelength. So first off, if I've got my wave, and I go ahead and I draw the wavelength on there, that was the wavelength, right? So my wavelength is right there, and I represent that with the Greek letter lambda, which is basically the Greek letter L. And so that symbolizes wavelength. Lambda is basically an upside down Y. I know it's a weird letter. You're just going to have to believe me on that. It's on the formula chart. So if you forget it, or you forget how to draw it, you can go ahead and look at it again. The other things that you're going to need to know are that right there, the time it takes to complete one full wave, up one wave, down the other wave. So that's one complete wave right here. One complete wave. That's one complete wave. That we label T, and that should stand for time, right? But it doesn't. It actually stands for period, which is just the time. And then we also have to talk about the frequency, which we represent with the letter F. Frequency is calculated by doing 1 over the period, so it's the inverse of the time. It's the inverse of time that the wave took. That's all it is. Here's all frequency means. If I draw two waves, I've got the one on the top only has 2 lumps, the one on the bottom has 4 lumps, okay? So if I ask you which wave is lumpy more frequently, the answer is the bottom one. So that has a higher frequency, that has a lower frequency. Now let's look at some longitudinal waves. So the longitudinal wave, the first thing you need to know about a longitudinal wave is it's really hard to draw. So I'm going to draw one. Don't laugh at my drawing, okay? So if you look on the drawing, it's kind of like a slinky, but it doesn't have to be a slinky. In a longitudinal wave, my motion is along the direction of the wave. So the wave is moving from left to right, just like the last one was, but it's not moving up and down. It's kind of bouncing like a spring back and forth along that left-right pathway. So the parts of this wave that we need to label are there. That's called the compression, because like the wave is all smushed up there. And then we have that part right there that's called the rarefaction. And I always kind of think of that in my head as that's the spot where it's not very squished together. The squishes are very rare there. It's spread out. So that's the rarefaction. And that's kind of the equivalent of the crest and the trough of the transverse wave. Those are the only two parts that you need to know on a longitudinal wave. You do need to know an example of a longitudinal wave, and an example would be a sound wave. So let's look at movement of waves. Waves can move in 3 different ways. The first is waves can reflect off of something. So if a wave reflects off of something, like if light reflects off a mirror, you know that it's going to hit the mirror and then bounce back at the same angle. So reflection is just the waves bouncing back at the same angle. The second way that it can move is called refraction, and that means that the wave bends when it moves from one medium to the next medium. What the heck does that mean? It means this. If I have light shining through the air and then entering a swimming pool, the wave bends as it moves from the air to the water because water is more dense than the air. So the wave will bend. So it was going at one angle, and then it's going to bend down to a different angle. That's just refraction. Refraction is how sunglasses work. Refraction is why also if you play those games with like the little pool toys where you go dive down and try and pick them up, sometimes they're not exactly where they look like they are. Or if you were to go spear fishing, I don't know why anyone would ever go spear fishing, but if you did go spear fishing, you can't aim at where the fish looks like it is. You have to aim away from that. So the last wave motion is diffraction, and that's where the wave bends around a corner. So let's say I've got a gap in a little wall there, and I've got a wave traveling towards it. That section of the wave is going to pass through. And then as the wave continues, it's going to get a little larger each time. So it's bending, but parts of the wall are going to block the wave. So that's diffraction. And that's it. That's all you need to know about the movement of waves there. What we do need to talk about other than that is the interference of waves. So you can have two types of interference. The first one is constructive, and this is pretty obvious, so we're not going to spend a lot of time on it. So let's say I have a wave, and I'm going to go ahead and have another wave, and they're traveling in sync together. So if I had those two waves in the same object at the same time, what would happen? Well, the answer is you would get a much bigger wave because they would build together. So you'd basically just add the waves together. That's constructive interference. They construct a bigger wave. Destructive interference is the opposite. So if I have that same red wave, but now I have an opposite blue wave, what's going to happen when I add those together? The answer is they're going to cancel each other out. So you subtract the waves from one another. That's it. If you have any questions, come ask Miss D.